Hey everybody, welcome back. We got some interesting material to cover today. I'm going back to the old Tech Talk style video, and we're going to dig right in to some in-depth information, and we're going to talk about a subject that is often really misunderstood in this industry. So go get yourself something to drink, get you some popcorn, get settled in. I'm going to try and break this up into two parts so that it's not so long, but we're going to dig into an interesting subject regarding distortion. We're going to look at all types of distortion, how we measure those distortions, and what do those distortions sound like. This is going to be a good one. Before I get started though, I want to give a thank you to Warwick. Warwick over in Australia sent me this really cool t-shirt. And I thank you very much. Got some crotch rocket racing going on there. That really gets good to me. That was a part of my life that I lived through, and it was a lot of fun. And I walked away from it at some point when I got married and never got on another one. And haven't missed it. It's okay. You know, I knew I couldn't keep going down that path. I was one of those guys that drag race those things. I would stand it up into a big wheel stand and ride a wheelie down the highway and, you know, just crazy stuff. And I lived through it. So looking at that shirt, Warwick, thank you very much. Brings back great memories. And I appreciate all of you guys who watch the videos, you hit the subscribe button, and you send me t-shirts and things. And I get tons of email and phone calls, and almost every call I get, thank you for the videos. You know, I appreciate the video, and hey, I appreciate all of you that watch. Now, let's dive into this thing. We're going to look at a lot of different types of distortion, and we're going to talk about the audibility of those distortions, and we're going to go through all the different types from the least egregious to the most egregious, starting with harmonic distortion, which is often really misunderstood. We're going to go through that. We're going to talk about distortions from time and phase errors. And when I say distortions, distortion technically is any deviation from the input signal. In other words, anytime you're altering the signal and changing it from what it was, you're distorting it from the way it was, and there's a lot of different ways that you can do that. That constitutes a distortion. So like I said, we're going to go right through them. After time and phase error distortions, we're going to look at surface reflection and diffraction distortions and how that is audible and what those effects are. We're going to look at stored energy, which is a really big one. And we're going to look at cabinet resonances, which is a huge form of distortion. And then one there at the end that I'm going to just surprise you with that I will have to say is the biggest and the most egregious form of distortion that there is. And so you're going to have to hang with us all the way to the end to find out which is the worst type of distortion. So, like I said, I'm going to try to break this up into two videos. I'm going to run through this on the fly. I don't have any notes other than some of the measurements and pictures that I'm going to throw in as examples. But this is all just going to flow as it comes to mind, just like it always does. I never rehearse this stuff. I never write anything down. I just have something on my mind, and I usually just lay it all out there in one shoot with no editing. So that's just the way it happens. Let's start with harmonic distortions. And this is a difficult one for a lot of people to understand. And you have to start with what are harmonics to begin with. And there are harmonics in almost all the different sounds and instruments and things that we hear. And what a harmonic is there's a fundamental that's at a specific frequency. Let's say a piano. Let's take a C note on the piano, and you hit that C note. Well, down low in output, much lower from the original note, we're going to have harmonics. And those harmonics are mathematical calculations of that C note. You can almost mathematically calculate over where those harmonics are going to be. It may be a C note an octave above or below, or it could be a combination of an E and a G or something like that that constitutes from that wavelength where those harmonics are going to be. So think of it as overtones. So you hear the actual strike of the piano, and there are sideband notes or side harmonics that are down low that help create this actual texture and the sound of that instrument. Some instruments have much greater harmonic structure than others. For instance, a flute may not have that much harmonic overtones. It's more very specific of that sound, of that wavelength that it's played. Whereas an electric guitar has lots of overtones, lots of harmonics that are really strong, and they may be really strong. Versus a human voice. A human voice has a specific frequency that it's at, and then it's got harmonics. And those harmonics help us hear what that actual instrument is, and it creates a little bit of that ambience and that sound that we recognize as what that instrument really is. Well, a speaker does much the same thing. So do amplifiers, and everything in some way or another can add some harmonics. Now with a speaker, this is a tricky deal. So we typically hit it with a full band of signal, and then we try to measure what those harmonics are, which would be like if it's excited at a certain frequency, what other frequencies are excited from that. So it's kind of acting the same way an instrument is, but we're trying to measure it in an odd way, really. We're hitting it with a full sweep, and then we're trying to see down in range, down in amplitude, what other harmonics are excited by what was played. And we typically look at those as a percentage of the fundamental. Like it will be a certain amount of percentage of total harmonic distortion, giving an average of what all of those harmonics add up to, or where the top levels of them are, how far they are down, based as a percentage. Now, it's really, really hard to measure those. I'm going to tell you right now. When we're measuring a speaker that's, let's say, playing at 90 dB, the harmonic distortion is going to be 45 to 50 dB down in level typically. That puts the distortion level at or below ambient room noise. So it's hard to measure that sound of those harmonics and that distortion when it's at or below ambient room levels. It's kind of like trying to measure a voice in a crowded cafeteria from across the cafeteria, and you're aiming at one person and saying, I'm going to measure that one person, but you got all this other noise going along with it. And you can't pick that guy up. It's just smooshed in with everything else. And when we try to measure harmonic distortion in a room, that's kind of what happens. It's almost impossible. You can put that speaker in an anechoic chamber, and you can get it to where that noise floor is just down to nothing. And then you can measure that speaker and see what those harmonic levels are and if they're a problem and things like that. Now, there are measuring systems out there like the Klippel that will take thousands of measurements all around the speaker, and it tries to make some differentiation from what was directly from the speaker versus what was reflected in the room. And it will go in and mathematically go in and gate out those late arriving reflections, and it'll try to isolate what came from the speaker and then which of those harmonics was coming from the speaker and separate that from the room noise and things like that. And to me, that's a bit of a stretch versus putting it in an anechoic chamber, but it may get pretty close. I don't know exactly what the level of accuracy really is, but there's some there that you can get an idea of what's going on. Now, at what value do we place on that? That's a whole different thing right there, but there is a way to get those measurements. Now, what a lot of people do that don't have a Klippel or something is they'll take that microphone and they'll run it right up to the very edge of the speaker, and they'll measure right at the speaker. So what that's doing is it's creating a big differential of what the speaker is playing, the output of the speaker, versus the room noise. So we're getting away from the room noise and getting right on the speaker. And you can take distortion measurements that way, but it's really not indicative of what's going on, because you're having to bring the level down really low. In other words, you can't play the speaker at 1 watt and put the microphone right on it. You'll max out the microphone. Like it can't handle that loud of a noise, even though it doesn't seem like it's that loud, but when it's that close to it, it's really loud. It's like taking a speaker that you think is not very loud, but sticking it on your ear. It's pretty loud. Same thing. So it's kind of like trying to measure the voice of a person in a crowded cafeteria, but you took the mic and you brought it right in front of him, and you put it right in front of him so that you could hear him more than everything else. So, yeah, you can do that, and you can get some validity there to the measurements, but it's not telling you anything because you're playing it at a fraction of a watt. You're not playing it very hard. You're not even causing the woofer or whatever you're measuring, the tweeter, whatever, to be stressed in any way. The clippal systems at least will allow you to take those measurements and then bring the power levels up, and you can see how those distortion measurements act with the speaker. Now, how does that sound? Like, I can tell you this, when you're measuring a speaker's distortion, and those distortion measurements are down around the 1 to 2, maybe even 3% range, it is really, really hard to distinguish those harmonics that the speaker is creating from the harmonics that are in the recording. In other words, all those instruments that are being played, all those vocals that are being introduced into the signal, all of those things all have harmonics that are all in there. And to try and pick those out from what the speaker is adding is really tough, because you just don't know which was in the recording and which was added. You just don't hear it. It's just all mixed in. You can't distinguish what that distortion really is. Now, when you bring power levels up to the point where things start going haywire, in other words, you're playing the speaker so loud that the voice coil of the woofer is spending more time out of the gap than it is in the gap, things like that, it will compress, it will lose control, and you will hear distortion. And that's with any speaker, any type, and it's the same with amplification. Back when I was a kid, they went through marketing wars where they would advertise distortion as if that related to sound quality. And they would say, our amp is 0.1% distortion. And then somebody would say, well, ours are 0.05%. And then someone else's company would come out, new, latest and greatest, 0.01%. I even remember some advertised as 0.005%. And granted, a lot of that solid state gear will measure to that level, but it really has nothing to do with how it sounds. There's a whole bunch of other things that contribute to how it sounds, and not just that, but it was a big part of marketing at that time. So we saw that a lot. Tube amps, on the other hand, tube amps could be 1% or 2% distortion. They were always much higher, but it added a rich harmonic texture that was not dry and sterile. A lot of people just gravitated to that natural sound of those tubes versus the harsher, staler sound of transistors and solid state gear. It was just really common, and still is. People love the sound of tube amps. They don't love it because it's distorted, but it does have a different harmonic texture to it, and it can, to many people, sound very much more real and very much more lively, and in ways that a solid state may just sound more dry. So you can't say that just because the distortion numbers are lower, it's going to sound better. It doesn't work that way. What happens is it only sounds bad when it goes south. And with a solid state amp, you can see the distortion measurements, which are fairly low, and then as you run out of power, the distortion goes up in a hurry. It all comes in all at once, and it clips. And you may even notice on a 100-watt amp, you're driving it at a 50-watt peak level, and then you get a big dynamic peak, and it digs down, and it needs that extra 50 watts of power. So suddenly it clips for just a moment, and you lose a little bit of your dynamics because it ran out of power. And used to, a lot of those old amplifiers would have clip indicator lights, or it would have meters on it so you could see when you were clipping. And a lot of guys just drove those things into clipping all the time. The lights, they'd bring it up to where the lights were flashing, and that's the levels that they felt like they could reach those levels and tolerate how that sounded without them staying on constantly. You know, it was a quick flicker, which it meant it ran out of juice momentarily, but just for a little bit. So it would just kind of round off the peaks, but it would still play really loud. Now, tube amps, on the other hand, clip very differently. A tube amp doesn't just completely distort all at once. A tube amp kind of clips much softer. We listened to one of my tube amps in here the other day, and we drove it to clipping, and we had the Aria set up, which were 85.5 dB sensitivity, and we had a 300B tube amp, which was 9 watts. And we brought the levels up to about the limit of the amp, and it was beautiful. And then as I tried to bring it up just a little bit more, it ran out of juice. That was it. That was all it had. And you can hear it compress right in the vocal region. The whole vocal region just compresses, and it distorts, and it loses all that beautiful magic that it had. And that's what happens when you hear harmonic distortion like that, and dynamic compression. A lot of that goes together. You're not going to notice harmonic distortions until it gets bad. When things really go south, you can hear it, and you know, I've pushed something too far, I've overdriven the speaker, or I've overdriven the amplifier, and it's usually the amplifier, and you know to pull those levels down. But you can't say, because this speaker has 1% and this one has 2%, that the one with 1 is going to sound twice as good. It doesn't work that way. It doesn't work that way at all. It's really, really tough to distinguish any of those harmonics from the music. Again, you can only tell when it really goes south. So I hope that made sense. And if you guys have questions on harmonic distortion, throw them in the comments section, and I'll see what I can do with it. Also, before I keep going, I want to say and give a shout out to Big J over at Jay's Audio Lab. Some of this is his fault. He told me the other day whenever I do one of these Tech Talk videos, he said to water this stuff down a little bit so that it makes sense. And in this whole video here, I'm going to be watering this stuff down to the point where people go, oh, yeah, I understand I get that now, that makes sense. And I don't want it to just go over everybody's head, so I'm not going to talk about all this stuff in a technical sense as much as kind of a common sense way. So, Jay, I hope you get it, and all the viewers out there get it. You know, I appreciate that feedback, and this whole video is going to be that way. And hopefully what I just went through on harmonic distortion makes sense. And it is easily the least egregious form of distortion of all the different types of distortion we're going to go through. Easily the least egregious. So from there, it's going to get a lot heavier, the distortions that we're going to go through. So let's start with, and I got some notes here. I'm going to throw up some graphs and some charts to illustrate what I'm talking about, so you guys kind of get it. We're going to look at time and phase distortions. Time and phase is when things are arriving out of time, or there's a phase shift there, and it's causing wavelengths not to line up anymore. In other words, you have the highs and then you have the lows behind it, and they're coming at you and they're out of time. And we see that a lot. We see it with drivers themselves in the crossover, where they're out of time or they're out of phase and they don't sum properly. And then we see sometimes where the offset of the voice coils are so far apart that it really disrupts time coherency. And we're going to talk about how that sounds. Let's start with a couple of speakers that I've measured that were really, really bad in this regard, where the drivers on axis just not in phase. Now, when I say in phase, I mean, let's say we've got a tweeter's response, and it rolls off, and well, you know what? Looking at it your way, it'd be this end. The tweeter's response rolls this way, and the woofer's response rolls this way, and they roll into each other. And what we want, where they cross, we want them to be in phase, and we want to see a 6 dB gain across the top. And for those of us who do this for a living, a lot of hobbyists, what we used to do, and what a lot of hobbyists would do, is do what's called a reverse null test, where they'd flip the polarity of the tweeter, and now they know it's going to be out of phase, but what they're looking for is they're looking for it to be out of phase and cause cancellation, and they're looking for a 15 dB hole. That means it's absolutely out of phase. Then when they flick it back in phase, they know it's absolutely in phase. So it's kind of a way to check. It's a way to flip between 0 and 180 and see if it goes from 0 to 180. And sometimes with the type of crossover you may have, the phase relationship may be 80 or 90 degrees phase rotation at the crossover point, and then they don't sum. In other words, they're not completely out of phase, but they're not in phase either. Anything around 90 degrees is like right in the middle. It didn't add up to anything, and the frequency response just follows the curvature of the tweeter and the woofer. Here's a perfect example. This was a Klipsch RP8000F. It's one of the worst measuring speakers I've ever measured in regards to phase at this type. So we're looking at the tweeter's curve and the woofer's curve coming together, and they don't sum. That means they're out of time. And then on the RP6000F, this was a similar model, but it had smaller woofers. We saw kind of the same thing. I want to say, in this case, they were about 80 degrees phase rotation, so about 80 degrees out of phase. So you see them drop, but they still don't sum very well. So it creates quite a hole in the response. So this creates distortion in two ways. One is it distorts the amplitude response, so there's a hole there. And two, there's still a time delayed response where they're not in time. So the way I would explain things not in time is, let's say we're listening to an acoustic guitar playing, and let's say the shift in phase is kind of like the Klipsch here. The woofer's voice coil is further forward than the tweeter's voice coil. The tweeter's voice coil is set further back. So you hear the body of the guitar, and then you hear the highs of the guitar, like the strings and the fingers on the strings, and it sounds like this. It sounds like two instruments. One's forward and one's behind it. There's a lag behind it, and it's disjointed, and it doesn't sound natural. It sounds messed up, and it messes up things within the sound stage right there. Things are not where they're supposed to be, and they're not coherent. There's a big disjointedness. That's a time and phase distortion, and it's real easy to hear, especially when you're used to a speaker that is very linear, and then you plug something like that in and listen to it, and you just hear a huge hole and realize that that's a major distortion. So let's also consider what happens as you move up or down. You see me in my videos talk about vertical off-axis responses quite a bit, and as you move up or down, the time arrival between drivers changes. And as it becomes further away in time, one versus the other, then it may be out of phase, and then it causes a huge hole in the response. And then where they're in phase, it may cause a big peak in the response somewhere. So I pulled up some that illustrated this quite a bit. There was a speaker that I had in here months ago that was a VMPS speaker. It was a VMPS 626R, and I want to look at the vertical off-axis on this thing. The red line, as you see in the measurement, is on axis, and we worked with this speaker a lot to find the best spot, and we worked with the attenuators that were on it to pull the levels way down and way up on the tweeter and try and get it balanced. And we got it to where, on that one spot where the microphone was, it was balanced. But watch what happens as we move up 4 inches per measurement. You see the orange line to the yellow line to the green line, and you notice a huge distortion from the signal. There's upper regions that completely cancel each other out. Down the lower region, some of it is starting to become more in phase, and it couples, and the response is just all over the place. And not only is the amplitude response all over the place, but the time arrival of everything is all completely disjointed as well. And in this case, it was so bad that I put the microphone back on the center axis there, and I move down 4 inches per measurement. And you can see it was really bad going that direction as well. So as you move up or down, everything becomes out of time. You had to stay just in that one little plane for you to hear everything in phase. So I know that a lot of you think, well, I'll just sit in that one spot and everything will be in phase. It doesn't work that way, because what you hear is a room reflection of all of that. So if the ceiling reflection or the floor reflection is completely out of whack, what you hear at the listening position can be completely out of whack too, because you're hearing a melt of all of the room reflections and the on-axis response. Some of those room reflections are delayed in time and create a sense of space and ambience, but you're going to hear some things way louder than other things, and it completely destroys what you're trying to do if you're trying to recreate three-dimensional sound. Now, let's look at one more to help illustrate this. This was a Klipsch Forte 1, which is a big speaker, and if you're looking at it from the side, we had a tweeter, voice coil alignment, and then we had the mid horn, which was really deep, and then we had the woofer, which was a little behind the tweeter. So let's look at the impulse response. The impulse responses here that you see, the first one that you see there was the tweeter, and then the little hump one, I think that one was in red, the little short hump was the woofer down below, and then that late arrival one that you see there in the measurement was the mid horn. So as you can see, those things are completely out of line in time. Now I can go in and I can create a crossover that catches at a certain wavelength, and then create a steep filter there so that they don't cancel each other out and they're in phase at the crossover point. So the sound sums flat, but there's still arrivals that are completely different. I'm catching one wavelength as it's completely maybe 1 or 2 wavelengths behind the other, and I'm catching them in phase, but they're still out of time. So when you listen to a speaker like that, if you're listening for imaging and soundstage layering and things like that, that type of distortion has wrecked that. So you may still like that speaker. You may be listening for its dynamics and how loud it plays, and you want a party speaker that you can just crank up with a group of people that are in the room and blast them out. And there may be a lot of different things you're listening for or you're wanting, and there's nothing wrong with that. But this is a time and phase distortion, and you can easily hear that if you've set this up properly and you're listening to the time arrival of everything within the soundstage. It gets really jumbled up and really messed up. So that kind of sums up time and phase distortion. I hope you guys can kind of grasp that. I know that's some of this is a little hard to digest maybe, but for some of you, you may just get it. So let's keep going right into the next one. It's along the same lines, and some of the same things are happening. This is surface reflections and diffraction. Now this is a biggie. This can have negative effects in multiple areas when you're listening to a speaker. So first of all, I'm going to show you some illustrations of some things that are really, really bad. Like I just went back and I found some pictures on the internet of some different things, some speakers. I don't even know whose these are. I just found the pictures, and they perfectly illustrate what I'm about to describe right now. So let's look at, first, this is a DIY speaker. I don't know whose it is, but it's on a great big wide baffle. And what happens is what you hear is not just what leaves the driver. What leaves the driver also reflects off of the surface of the front baffle, and it reflects forward. It's kind of like people say dropping a rock into a pond and you see the ripples spread out in a circle in all directions. Well, that's like a two-dimensional illustration of what we're hearing. If you tip that up and it was a sphere, that would be more of a three-dimensional reflection of what we hear. We hear it radiating in all directions. And as frequency decreases, those low frequencies will completely wrap around the enclosure, and it goes to the back of the room, and it's omnidirectional. All right, I went over 30 minutes and I saw the camera automatically click off, so I had to jump up and turn it back on. So picking up where I left off, as frequency wavelengths get shorter, it becomes more directional. In other words, the signal is just from the baffle forward. But somewhere in between there, a lot of those ripples are going to reflect off the baffle. It's like taking a great big sheet of wood and putting it down in that pond and dropping the rock right down next to it. And you see those ripples as it splashes into the water. Those ripples reflect off of that sheet of wood, off of that wall that you've created, and they start reflecting forward. And so what you hear isn't just what leaves that driver, but also what reflects right off of that surface and sometimes off of the edges, especially if you have a sharp edge. Like if you have a driver that's not flush mounted, but it's surface mounted and there's a drop off there, sound is going to reflect right off of those edges and it's going to cause diffraction. Same way out at the ends of the cabinet, you have a sharp edge or you have side walls, like on some of these vintage speakers that stick out. Sound is going to reflect right off of that and cause a lot of diffraction. Here's another perfect illustration. I don't know what speaker this is, but it's a big open baffle speaker. Again, great big baffle, multiple problems here. You've got a tweeter mounted right in the middle of a great big baffle. That means surface reflections on the left are going to match the surface reflections on the right. All the amplitude peaks are going to line up in the same place, and you're going to get great big peak. It's especially bad when it's centered from the top, kind of in the same way. You can wind up with reflections in 3 different places at the same frequency, and that really causes a big peak. Another thing I noticed on that speaker was the tweeter was surface mounted, so you got diffraction coming off of there. You got diffraction from the edges of the cabinet, and then of course the acoustic centers are way too far apart. So fail, and fail. Just looking at that, there's a whole lot of distortion that's going to be caused just because of this, just because of the way it's designed. Now, let's talk about what some of that sounds like. When those wavelengths reflect off of that surface and come forward, it sounds very localized. In other words, you're not just hearing the sound from that speaker, but from that whole baffle. And the wider and the bigger it gets, the more it sounds like it's playing from that baffle forward. Simple, pure physics of it. There's no getting around it. That's what happens. So it causes changes in amplitude. Like it can cause peaks in the amplitude, and the diffraction there and can cause dramatic peaks, and those arrive later in time. So there's time and phase distortions as well. So we've got distortions in amplitude and distortions in time and phase. So there's multiple distortions taking place from those great big baffles. And let's look at some old school speakers, because these were real egregious. They were horrible when it came to that. Let's look at this old JBL. These drivers were not countersunk in there either. They're just all surface mounted, reflections off of all of them. It had a frame around it that stuck out so the grill could set into it. Sound reflected off of that stuff horribly. That one was so bad I couldn't even do anything with it. I was like, oh, this is awful. Here's another, the Pioneer HPM 100, a very popular speaker. I was able to straighten that thing out, and I can't fix all those reflections. All those reflections and all that diffraction is there. What I have to do then is go in and create notch filters and things within the band pass of each driver and try to keep each driver in a range to where it's not as affected as if it were playing an octave or two higher or lower, and try to keep it in a range that minimizes some of that. And all those notch filters are doing is they're taking the peaks and they're turning them down. They're pulling them down, they're lessening it, and they're balancing out the sound. I can get a balanced frequency response. And if you look at what I did with the HPM 100, you think, man, I waved a magic wand across this thing. That frequency response was totally jacked up. And I designed a new crossover, and I flattened that stuff out nice and smooth. And you think, wow, that's going to sound just like speaker right over here that's nice and smooth. He makes all the speakers sound the same. They all have a flat response. Has nothing to do with how the speaker sounds. That all that has to do with is with how accurate it is at that one plane. That's all that represents. The frequency response measurement is a drop in the bucket. You have to look at all the other things involved, and all those surface reflections and all that diffraction from the edges all constitute distortions of the original signal. In fact, let's look at a spectral decay of the HPM 100. This was the stock frequency response, and I want you to look at all these long lines that are trailing out from this spectral decay, and you can tell that those are surface reflection issues and diffraction issues because you see the top line and you see it starting to drop off pretty well. It's nasty. There's peaks there, but you see it drop off and it comes down a little bit, and then you see those traces come way out there like that. And sometimes those little traces don't even line up very well with the peaks that are amplitude peaks. So we know those are secondary arrivals, and it's reflections off of the baffle, it's diffraction off of the edges, and it's a distortion of the original signal. It's a time and phase distortion, and it's changing the amplitude as well. So it really is wrecking the response. Even when I go in and I create corrections for the amplitude, we've got amplitude corrections, but I've still got time and phase distortions that are going on because those reflections are still there. Let's look at a few more. There are a few companies out there that have decided to do some old school speakers, and they look like the old speakers, but they're new and modern, and they've got better drivers in them, and the parts quality is usually better. Here's a couple of examples. Let's look at the Wharfedale Linton. I notice, it's still got that old school look. It's still got the edges that stick out, and it's got drivers that are kind of right up the middle of the baffle. So we've got a lot of surface reflection, and we got a lot of diffraction. So, and that's going to totally wreck the response. There's just no getting around it. It's going to cause time and phase distortions. And those are a lot easier to hear by far than total harmonic distortion. The harmonic distortion is nothing compared to the distortions that this is going to create. This is going to cause localization of the sound. It's going to completely disrupt the sound field, imaging, layering, all of that stuff is completely disrupted because we're throwing in time elements. In other words, that reflection is delayed in time. So you hear, like if the baffle is here, here's the driver, and then here's the reflection off of the edges out here. It's further away in time, and because it's further away in distance. So it's arriving right behind the original signal, and it's causing a disturbance there. It's causing think of it as like a drum hit. Instead of a one hit, it's a hit like that. It's a smear or a blur of the signal. In fact, let's look at another one here, the KLH Model 5. Now the KLH Model 5, it's an old school design like that. Same surface reflection. Drivers are right up the middle, and it's got the edge diffraction going around the outside edge. They went in and designed a crossover that somewhat balanced out the response. Let's look at the frequency response on it. You can see there's some choppiness there, but the overall average is not too bad. So let's look now at the spectral decay, and you can see the drivers are dropping off nice and clean, but then after it's dropped off a little bit, see all those little fingers out there? All that secondary coming at you there? That's pretty much all reflections off of the surface and diffracting off of the sides, and it will wreck it in the way we listen to, again, all those time elements. I'm going to look at one more, and this will be the final one that we're going to look at. And I've illustrated this one a little bit better. This one I did an upgrade on a little before Christmas of last year, and we just launched videos on it this year. This was a Wilson Watt Puppy 8, and it's a pretty nice speaker. There's really great aspects about this thing. I mean, the Wilson speakers are really, for the most part, pretty well engineered, really well made. But the Watt Puppy had some issues. The front baffle around the drivers was foam, and then there was a rim that stuck out all the way around it. Like the front baffle had like the sides stuck out past it, then the drivers are mounted in there and there's foam around it. But the sound reflected off of those edges and it caused significant diffraction. Now I'm going to illustrate what I was telling you about when I said that those are time and phase distortions and it causes amplitude distortions, and I'm going to try to explain why. Let's look at the measured frequency response of the tweeter with no crossover on it, okay? No crossover, measured frequency response. It looks rough. I mean, that's a rough frequency response. In fact, let's look at the frequency response of the whole crossover. This is after they put a filter on it to try and correct it, and you can see it's still really, really rough. Now, let's throw up another measurement of the frequency response with no crossover on it. And one line you can see there still looks the same. It's still really rough. And the second line that runs through there, a different color, looks nice and smooth. That's when I took the grill and I put thick row of felt all the way around the grill so that it did away with those diffraction, that was coming off of the edges of the baffle itself. When I did that, it smoothed right out. So if you look at that line and then you compare it to the one before, you can see that there are some peaks there that it knocked down. Excuse me. And there is a dipped area that it brought up. Right about, just below 2,000, there's a huge peak. And right up there just above 4,000, there's a big peak. And then right at 2,800 hertz, there's a great big dipped area. So let's explain what's going on there. So the output from that tweeter, it's coming out and it's going off to the sides and it's reflecting off of those edges and it's coming forward. And it's coming forward delayed in time versus what's on axis. In other words, this reflection over on each side is further away in distance, so it's further away in time. And when it arrives, it's out of time with the tweeter's output that's coming directly from the tweeter. So where you see those peaks, that's where it's arriving, where those wavelengths line up, and it's in phase. In other words, it's kind of like it made a megaphone. It compressed or it added to, you hear the tweeter plus the reflection, and now it made it louder. But where that dipped area is, right like at 2,800 hertz, those wavelengths arrived out of phase. So it reduced the output, what was coming straight from the tweeter, plus the time arrival of the reflection was out of time, and now it created a hole. So now we have a response that's completely jacked up. Now, in the crossover that they put on there, they didn't correct for all of that stuff, and the reflections are there. So what does it sound like? What does it do to the sound? Well, it's a time and phase distortion, and it's an amplitude distortion. So it's messing up the amplitude, and it's messing up the time arrival. Messing up the amplitude means it's louder than it's supposed to be in one area, and it's quieter than it's supposed to be in another area. That's a deviation from the original signal. The time and phase element, though, can be even worse because it messes up all the imaging in the soundstage layering and where things are and depth of sound field, because those things are out of time. And for things to be placed within the soundstage, they have to arrive in time. I know a lot of people will say, well, I've heard that speaker. It images great. And in some areas, it may image really great. The vocal region isn't affected by that, and the vocal may be center planted right there, and a lot of the fundamentals that you hear are imaged very well. But a lot of these overtones and things that are the upper level harmonics are destroyed by the time element, the time distortion, and the amplitude peaks. It messes all that stuff up. So the imaging and the soundstage layering may not be near what it could be. And these distortions are extremely audible. It's like people act like sometimes when I'm working on a speaker and I'm correcting it for all this stuff, they say, you're just changing the voicing from one thing to another. That's how the original person wanted the voicing. It was voiced like this. You're just changing the voicing. Who knows whether that voicing sounds better than this voicing? And none of that is true. None of that's true. I'm not changing the voicing. when I'm doing an upgrade on something, I'm correcting problems that are audible distortions. And it's not subjective. You know, the original designer didn't design something to have time and phase distortions because that's part of the voicing. That's not voicing. Voicing is when we see a change in amplitude over a range. Like take ATC speakers, for instance. We've had several of them in here, and they're voice soft on the top. In other words, the bass response is here, and the tweeter level is a little down. That's voicing. We see speakers that have a BBC dip right at the crossover region. We see a little softer area there. They voiced it that way. Amplitude variations from top to bottom could be considered voicing. Time-delayed distortions are not voicing. Diffraction elements, distortion in that regard, that's not voicing. Amplitude problems from those time arrival issues, that is not a choice that someone made and said this is how we wanted it voiced. Those are amplitude errors. So I want you guys to kind of be aware of kind of what some of these things are and what we're working on when we get some of this stuff in. Now, that's going to wrap up this little episode here. I've got 3 more types of distortions that we're going to talk about in the next episode, and we'll drop that maybe the next day or in a couple of days. So stay tuned for that. It's going to be a good one too. We're going to get into the most egregious types of distortion that there is. So hang in there, and we'll see you guys in the next video.